Force on a current-carrying conductor. Welcome back to yet another interesting module. In the previous modules, we learnt that an electric current flowing through a conductor produces a magnetic field, and this field exerts a force on a magnet placed in the vicinity of the conductor. But the story doesn't stop here. Just think, will not the magnet do the same? Yes, according to a French scientist, André-Marie Ampère, the magnet also exerts an equal and opposite force on the current-carrying conductor. Let's demonstrate this with an activity. Take a small copper rod AB and suspend it horizontally from the support using two connecting wires. Then connect it to a circuit in series with a battery and a switch. Place a strong horseshoe magnet. Ensure that the rod should lie between the two poles of the magnet, with the magnetic field being directed upwards. This can be possible only when the north pole of the magnet is below and the south pole is vertically above the rod. Close the switch and allow the current to pass through the rod. Now observe carefully. The copper rod is displaced towards the right side. Open the switch and reverse the current by changing the polarity of the battery. Again, repeat the same procedure and observe. We can see that the conductor is now displaced towards the left side. What could be the reasons for such displacements of the rod? It means a force must be exerted on the current-carrying copper rod when placed in a magnetic field. Changing the current direction also reverses the direction of displacement of the conductor. Now let us check what will happen if we reverse the direction of the magnetic field, which means changing the field vertically downwards. Will it give the same result? Let us perform the same experiment by reversing the positions of the poles of the magnet. It has been observed that the direction of force acting on the current-carrying rod also gets reversed. What will happen if we increase the supply voltage? The displacement also increases. From all these experiments, it has been found that the direction of displacement of the current-carrying conductor depends on the direction of the current and the direction of the magnetic field. The displacement of the conductor is largest, or the magnitude of the force is the highest, when the direction of current is at right angles to the direction of the magnetic field. The relationship among the directions of the current, magnetic field and displacement is explained by Fleming's left-hand rule. Let us illustrate Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand in such a way that they are mutually perpendicular to each other as shown. If the forefinger points in the direction of the magnetic field and the middle finger in the direction of the current, then the thumb will point towards the direction of motion or the displaced force acting on the conductor.